In today's lesson, we're going to focus on the fundamental theorem of algebra and some other theorems that help us find the zeros or the roots of polynomials. So if f of x is a polynomial of degree n, so that means you have at least x to the first power, which would be a line, or you could have a quadratic, etc. Then f has at least one zero in the complex number system. And what it's important to understand is, remember, the complex numbers consist of real numbers and imaginary numbers. And then we have a linear factorization theorem, which sounds fancy, but it really isn't. It just says if f of x is a polynomial of degree n, where n is greater than 0, so that means you have at least a line, then f has precisely n linear factors. And that's important because then that tells us, therefore, that there will be n zeros. So, for example, a polynomial of degree 2 means there's going to be 2 zeros. So when you have a quadratic, you have 2 zeros. Now, if you're thinking of the graph, that means the graph is going to cross the x-axis at 2 places? Well, not necessarily. If it does, then you have 2 real zeros. If the vertex is on the x-axis, you have 1 real zero, and it's going to have multiplicity too. And then if it doesn't go below or it doesn't hit the x-axis, that just means that you're still going to have 2 zeros, but they're both going to be imaginary. So if you have a polynomial of degree 5, there's an x to the 5th polynomial, that means there's 5 zeros. Some might be real, some might be imaginary. All right, now unfortunately, these theorems just tell us how many zeros there are, but not how to find them. So let's look at some examples. Find the zeros of f of x equals x to the 5th plus 9x cubed. Well, the first thing we could do is we could set it equal to 0 and try and factor. And we can factor out an x to the 3rd power, and that would leave us with x squared plus 9. So therefore we know that x is equal to 0, or x squared plus 9 is equal to 0, which means x squared is equal to negative 9. So that's not going to be a real solution. And then when I take the square root of both sides, I get the absolute value of x, we've talked about that before, equals 3i. So therefore x is equal to plus or minus 3i. So the zeros for this function are 0 plus or minus 3i. Now, you're looking at that and saying, well, there's only 3 zeros. Actually, x equals 0 is a root of this function, but it has multiplicity 3. And I could think of the factorization of this as being x times x times x times x squared plus 9, or x minus 3i, x plus 3i. And so there are 5 factors, and there are 5 zeros, but one of them has multiplicity 3. Let's look at another example. And this is really going to put together everything that we've learned so far. All right, find the zeros of this function. So factoring is probably not going to be very helpful, but let's use some of the ideas that we've learned. I know by looking at that 8 and the coefficient of x to the 5th is 1, I know the possible zeros, my possible real roots, are going to take on the form plus or minus 1, or plus or minus 2, or plus or minus 4, or plus or minus 8, all over plus or minus 1. That was that p over q idea. Any factor of the constant term divided by the coefficient of the leading term. All right, so that narrows it down for us at least, and then dividing by plus or minus 1 really means that we have 2, 4, 6, there's only 8 possibilities. Either plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. All right, so let's try one. And actually, before I do that, let's think what else we've learned. How many sign changes are there for g of x? Well, we go positive 1, Then we have another positive, okay, so we switch positive to negative there, that's one sign change. And then we switch back to positive. So we have two sign changes, which tells us, for our function, that we have 2 or 0 positive real roots. Okay, and then what else did we have to do? Well, then we also had to look at g of negative x, and to the 5th power will give us a negative x to the 5th, and we'll have a negative x to the 3rd. Squaring it's going to leave it as positive 2x squared. This will become a positive 12x and a positive 8. So how many sign changes do we have here? Well, we've got a negative, negative, so there it switches to a positive, and then it never switches again. So we have one sign change, which tells us, for g of negative x, that there is one negative root. So we know we have at least one negative root. Actually, we know we have, at most, we have exactly one negative root. So out of those 8 choices of my possible roots, let's try negative 2. And I'm going to use synthetic division. So if I write down my coefficients, I have a 1. There's 0x to the 4th, don't forget that. 1x to the 3rd, 2x squared, negative 12x, and a positive 8. So I'm going to do synthetic division, and hopefully I get a remainder of 0. If I don't, I cross that one off, and I'll try another one. So bring down the 1, multiply by the number in the box, add those together. Multiply by the number in the box, add those. 5 times negative 2 is negative 10. Gives me negative 8. That's negative 16. Oops, positive 16. That'll be a 4. 4 times negative 2 is negative 8. Perfect. No remainder, which means x plus 2 is a factor, and x equals negative 2 is a 0 of this function. All right, so I found one of them. So x equals negative 2 is a root, or a 0. All right, so what do I have left? Well, from there, I've got 1x to the 4th minus 2x cubed plus 5x squared minus 8x plus 4. So now I need to work with that. So I know that I've got one negative root. So that's taken care of. I also know that I have 2 or 0 positive roots. So let's try a positive one. I could do 1 or 2 or 4 or 8. Let's try a 1. And you know, if it doesn't work out, if you get a remainder, look in here, if you get a remainder, then that's not a possibility, you try another one. All right, so now let me try a positive 1. And I have coefficients 1, negative 2, 5, negative 8, and 4. And I'm hoping for a remainder of 0. So I bring down the 1, multiply by 1, I get 1, add those, multiply, add, multiply, add, multiply. Perfect. I found another one. So I know that x minus 1 is a factor, and that x equals 1 is a root, or a 0. Okay, so I found 2 of the zeros. Now that I found one positive root, I know that there's not 0 positive roots, so there has to be another positive root. So let's see where we're at. Let me move this over. So what I have down here is I have an x cubed minus an x squared plus 4x minus 4. So far this polynomial g of x, I can write as, I know x plus 2 is a factor. That was my first synthetic division. I know x minus 1 is a factor. And then I have left x cubed minus x squared plus 4x minus 4. And now I can try another one. I could try a positive 2 or a positive 4 or positive 8 or maybe another positive 1. But I can factor this one by grouping. I can factor out an x squared from the first 2 terms, and I'm left with x minus 1. And I can factor out a 4 from the last two terms, and I'm also left with an x minus 1, which therefore means I can factor out an x minus 1 from both of those, and I have x squared plus 4. So now I've found all the factors for this polynomial, g of x. And notice that x equals 1 is a root of multiplicity 2. So finally I can write all my zeros. My zeros are, if x plus 2 equals 0, that means x equals negative 2. If x minus 1 is 0, that means x equals 1. And that one has multiplicity 2. And then x squared plus 4, that means that x is going to equal plus or minus 2i. And so there's all my zeros for this function. If you look at the graph of this function on your calculator, you'll see that at x equals 1, the graph comes down and bounces off the x-axis at 1. So when the multiplicity is even, that means that your graph is bouncing off the x-axis at that point. All right, let's look at another theorem. If f is a polynomial function that has real coefficients, and then if a plus bi, where b is not 0, so we have an imaginary number, if that's a 0 of the function, then its conjugate is also going to be a 0 of that function. So imaginary roots come in pairs with their conjugates. All right, so how does that help? Okay, so let's look. Find a 4th degree polynomial, 4th degree. So we need an x to the 4th polynomial with real coefficients that has roots -1, -1, and 3i. Well, from this theorem we know if 3i is a root, then so is -3i. So remember, it's 0 plus 3i is one of the roots, so the conjugate is 0 minus 3i. All right, so if we know all 4 of the roots, then we can write our polynomial. If x equals -1, that means that x plus 1 equals 0. So one of my factors is x plus 1. And then -1 is another 0, so another x plus 1. And then 3i, and let me write this over here. So if x is equal to 3i, then that means x minus 3i is equal to 0. So that's another factor. And then x plus 3i. So there's my 4th degree polynomial. The convention in this type of a problem is that you need to multiply this out so it's in that standard polynomial form. X to the 4th, something x to the 4th plus something x to the 3rd, etc. So let's go ahead and multiply this stuff out. X plus 1 times x plus 1 is x squared plus 2x plus 1, if you distribute correctly. Now for the next one here, we're going to have an x squared. It's the difference of two squares. We're going to have x squared. We'll have a plus 3xi and a minus 3xi, which will cancel, and then minus 9i squared. But remember, I squared is -1, so that's really x squared plus 9. And now I need to multiply these two, combine my like terms, and I'll be done. So let's start with the x squared term, multiply it by everything. I'm going to get an x to the 4th plus 9x squared. Notice I left a space there. Now I'm going to go ahead and multiply the 2x, and I'll get 2x to the 3rd plus 18x. And finally, I'm going to distribute the 1 with the other terms in the parentheses, and I get 1x squared plus 9. So, not many like terms here. So my final answer is x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9, unless I made a mistake. And let me check. I don't think I did. So that looks good. So this is my function. Now obviously I could have multiplied this by any constant in front here, 3 or -7 or whatever, but keep my life simple, and I won't do that. So I'm just going to leave it like that. All right, 2 more examples. Find the quadratic function h with real coefficients that has 2 minus I as a 0, and also h of 2 is going to equal 3. So we'll worry about that later. Let's focus on what we're trying to do. We need a quadratic. We know 2 minus I is a 0, therefore 2 plus I is also a 0. So I have x equals 2 minus I and x equals 2 plus I are both zeros, so x minus 2 plus I is equal to 0. That'll be one of my factors. And x minus 2 minus I will equal 0. So this function, h of x, is going to equal potentially some constant, could be 1, could be something else, and then my factor is x minus 2 plus I and x minus 2 minus I. So let me multiply this out. X times x gives me an x squared, and we have a negative 2x minus xi minus 2x plus 4 plus 2I plus xi, or ix, minus 2I, and minus I squared. So let's combine some like terms. I only have one x squared term. I have a minus 2x and a minus 2x, so I have a minus 4x. I have a minus xi cancels with the plus xi. The positive 2i and negative 2i cancel. Minus I squared is minus a negative 1, so plus 1 plus 4 is plus 5. Okay, so here's my function so far. Now let's go to the other information. H of 2 should equal 3. So 3 should equal...
Good morning, Iowa High School. Is Mr. Rosh call?